Hi, my name is Tiagi, and in this video, I'll be going over trig substitution for integration, which is an important technique for Calculus 2 and Calculus 3 students. So the purpose of trig substitution integration is obviously to solve an integral, and we use it when we have a piece in our integrand that's in the form of either square root a squared minus b squared times x squared, or b squared x squared minus a squared, or b squared x squared plus a squared. And if we're not able to use u sub, integration of parts, or we can't just use simple inverse trig integral rules. So when we have a piece in our integrand that looks like this, this, or this, more than not, if we're not able to use any of these, we can try using a trig substitution. And the idea is, with the trig substitution, what we want to do is we want to take this square root function, which is kind of complicated, right? We have a square root, we have some x, and you want to turn it into a neat, simpler trig function in terms of theta. Once we have it in terms of theta, we then integrate it, and then we finally plug back into terms of x at the end. So that's the general idea with trig substitution, but how do we actually do it? So let's start off with an example. Let's say we have to integrate the function square root of 1 plus x squared dx. So obviously here, there's nothing we can do with u sub, integration by parts, or anything else. We're going to have to use trig sub, which works in a squared plus x squared is in that format. So the first step is we want to draw a triangle, a right triangle, and we're going to label our triangle based on this. So we can see here, the Pythagorean theorem, right? A squared plus b squared equals c squared. This part, square root 1 plus x squared, that has to be the hypotenuse, because again, this is a squared plus b squared. We have square root 1 plus x squared here. And let's label this angle here theta. So the rule is, whenever we're doing a trig sub, we want to get our theta function, right, in terms of either sine, secant, or tangent. And we want it to equal x over a. We want it to equal x over a. So here we have two options, right? Because 1 or x could be either leg. It could be x here, or it could be x here, right? But we want to get our theta function, right, sine, secant, or tangent equal to x over a. So let's say, what if we did sine? So if we did sine of theta, we put x here, right? We get x over square root 1 plus x squared, which isn't x over a. If we put x here, we would get 1 over square root 1 plus x squared, which is x over a. So what can we do? Well, what if we put x here, 1 here, we get the tangent of theta is equal to x over 1, right? Opposite over adjacent, which equals x. So that's the function we're looking for, tangent theta equals x. Next, we're going to take the derivative, because if we want to put it in terms, this function in terms of theta, we still have a dx. So we'll take the derivative, we get the dx is equal to the secant squared theta d theta. Okay, so now with these, we'll plug it into here. We'll get that we have the integral of 1 plus x, right? X is tangent theta, tangent squared theta, right? Dx is equal to secant squared theta d theta. We know from Pythagorean identities, 1 plus tangent squared theta is equal to secant squared theta, right? So the square root of that is going to give us secant theta. So secant theta times secant squared theta is secant cubed theta, d theta. And so now we have to integrate this, and what you'll notice is we can actually use integration of parts for this integral. So secant theta times secant squared d theta is how we'll break it up. You'll see that if we have dv equaling secant squared theta d theta, we can make our v simply tangent theta, right? Because the integral of secant squared theta is tangent theta. Next, we can then make our u, therefore, right, u dv, it has to be equal to secant theta. And we know that the derivative of secant theta is going to be equal to secant theta tan theta d theta. Okay, let me just clear up some space. So we know, therefore, that the integral secant theta d theta equals uv, so secant theta tan theta minus the integral of v du. It should be du, not du. So v du is tan theta, secant theta, tan theta, so secant theta, tan squared theta, d theta. We can't do any u sub here, so we have to do is we say that, okay, tan squared theta, based on the Pythagorean identity, right, 1 plus tan squared theta is equal to secant squared theta. Therefore, tan theta is equal to secant squared theta minus 1. If we plug that in and we expand, we'll get that the integral, right, so secant cubed theta d theta, right, because secant squared times secant theta, minus the integral of secant theta d theta, right, because we have 1 minus 1 times secant theta is minus secant theta d theta. Okay, so here we can see that this, let me just erase a little more. And again, this integral equals here secant theta d theta. Okay, and so from here we see that, okay, secant cubed theta d theta is equal to secant theta tan theta minus, again, we don't know what this integral is, secant cubed theta d theta minus integral of secant theta, which we know to be the ln of secant theta plus tan theta. And so you can see here that we have two integral. We have integral of secant cubed theta d theta, integral of secant cubed d theta, right? Same thing. And so we can move this term over here. We get that 2 integral of secant cubed theta d theta is equal to the right-hand side. And then we divide by 2. And what we get is we get the integral of secant cubed theta d theta is equal to 1/2 secant tan theta, right? Just right-hand side, minus 1/2 ln of secant theta plus tangent of theta. And of course, this secant cubed theta d theta equals our original function. But the issue is our original function is in terms of x. And so to get the answer finished, we have to get this term, which equals our answer, in terms of x instead of in terms of theta, because our function originally is in terms of x. So from right off the bat, we can see that tangent theta equals x, so we can plug it into here and here, but we need to find secant of theta to plug it back. So looking at our triangle, we can see that secant of theta, right, so 1 over cosine of theta, is going to equal to square root of 1 plus x squared over 1, which is just square root of 1 plus x squared. So now we have all the tools to plug in these two expressions back into here to get the answer in terms of x. So if we do so, we get 1/2 secant theta, which is square root of 1 plus x squared, times tangent theta, which is x, minus 1/2 times the ln of secant theta, which is square root of 1 plus x squared, plus tangent theta, which is x, and obviously plus c because it's an indefinite integral. So that's an example of how we use trig substitution to solve an integral. And I guess just to go over the general steps of what I did here, the general process to solve any kind of trig substitution is to first recognize one of the expressions that I listed before, right? So the square root b squared x squared minus a squared, or one of those. Then after you recognize one of the expressions, you have to draw a triangle and get the integrand in terms of theta. And finally, you integrate. And after you integrate, you get your function back in terms of x, like you just did right now. Okay? So I just showed you guys one case with square root 1 plus x squared, so the case where it's adding. What about the other two cases that I listed before? So we'll go over those quickly. So if we have the case square root b squared x squared minus a squared, right, we draw our right triangle. We know from the Pythagorean theorem that b squared x squared has to be our hypotenuse, right, because it's positive, which means that a and 1 are going to be our legs. Okay, and again, we want it in terms of sine, secant, or tangent. And so in this case, if we put our a to be here, and our 1 to be here, we can say that secant theta is equal to bx over a. And therefore, bx is equal to a secant theta, which we can then plug in there once we have the d thetas. And finally, the last example is if we have a squared minus b squared times x squared. Draw a triangle again. In this case, the hypotenuse is a because it's positive. Theta is here, right angle. And so in this case, how can we get it in terms of bx over a? Well, if we do sine of theta, right, we set this part to be bx, this part to be 1, we get that sine of theta is equal to bx over a. And we get a similar expression that bx is equal to a sine theta, which we can then plug in to here once we take the derivative as well. Let's just do one more example just to see another type of trig substitution, and then we'll be done for this video. So let's say we're taking the integral of 9 minus x squared over x squared dx. Okay, so first step, right, we recognize that this is a trig substitution problem, right? We can't do u sub, and we see that this matches one of our known integrands. So we draw a triangle first, right? Our triangle is going to look like this, right? 9 is positive, so that's hypotenuse 3. This is theta. And we can see that it matches the form that sine theta, right? So opposite, we'll make this x, make this 1. So sine theta, x over 3. And then the derivative, right? So actually move it over. So x equals 3 sine theta. The derivative of this, dx, is going to equal to 3 cosine theta. Now we're going to plug it back into here. We get that the integral of square root 9 minus 9 sine squared theta, right? So x is equal to 3 sine theta over x squared, which is 9 sine squared theta, times dx, which is 3 cosine theta d theta. Okay, so we integrate. First thing here, we can see that this is the same thing as 9 times 1 minus sine squared theta, which if we know our Pythagorean identity, right? Sine squared plus cosine squared equals 1. Therefore, this is just square root of cosine squared theta, or sorry, square root of 9 cosine squared theta, which is equal to 3 cosine theta on the top times 3 cosine theta, derived from this expression, over 9 sine squared theta d theta. And so we can see that the 3, 3, 9 cancel out. Cosine theta times cosine theta is cosine squared. Cosine squared over sine squared is going to give us integral of cotangent squared theta d theta, right? And so we know from identities that 1 plus cotangent squared theta is equal to cosecant squared theta. And so therefore cotangent squared theta is equal to cosecant squared theta minus 1. So this is the integral of cosecant squared theta d theta minus d theta. So cosecant squared theta is going to equal the negative cotangent theta, and this becomes minus tangent, or sorry, minus theta plus c. So that's our integral, right? That's what we evaluated as our answer. But again, the issue is we want to get in terms of x, right? Because our integral is in terms of x. So we need to find what cotangent theta equals. Well, from here, cotangent theta is going to equal, right, adjacent over opposite. So it's going to equal to, oh, sorry, this shouldn't be 1. This should be, right, so this is x, this is 3. That can't be 1, obviously. It has to be 9 minus x squared. Sorry, I've been labeling my diagrams wrong. But this this term has to be 9 minus x squared. It's not 1. I messed up before. It was 1 in the original problem, the first one. But here it's just going to be this, right, to make the Pythagorean theorem work. Okay, so cotangent theta is equal to adjacent over opposite. So square root of 9 minus x squared over x. So we plug it into there. So it's negative 9 minus x squared over x minus theta. So we have here sine theta is equal to x over 3. So theta is equal to the inverse sine, or arc sine of x over 3, minus arc sine x over 3 plus c, and that's our answer for this integral. And yeah, that's how you do trig substitution for integration. Thank you all for watching, and I hope you had a good time watching this video. And I'll see you guys all tomorrow. Bye.